Hello everyone. This is the solution to the problem set given to the students at the Tech de Monterey. It is a classic engineering problem involving the flow of vapor through a turbine. We will be answering what is the water vapor's temperature when it leaves the valve, calculate the vapor quality in the outlet of the valve considering the water vapor is humid, and is it possible to determine the thermodynamic state of the vapor in the outlet of the turbine only with this information. To start off, it is helpful to draw a diagram of the system and to note the conditions given. At the entrance, we have a mass flow rate of 5,000 kilograms per hour, a pressure of 4,000 kilopascals, temperature 300 degrees Celsius, velocity 60 meters per second, and height 0 meters. At the discharge, we have a velocity of 200 meters per second and a height of -3 meters. The system experiences work of 570 kilowatts and an energy release of -135 kilojoules per minute. Take a moment to review the concepts of the open system, the first law of thermodynamics, including delta U equals Q minus W, vapor quality, and steam tables, as they are all relevant to this problem. On our way to solving for vapor quality, we can use the expansion of delta U equals Q minus W. This equation, Q minus W equals M times the quantity of delta H plus delta P plus delta K. But first, we have to make conversions. Q now equals -2.25 kilojoules per second, W equals 570 kilojoules per second, and mass flow rate equals 1.38888 kilograms per second. Delta P is given by gravity times the change in height, and delta K is given by 1/2 times the change in velocity squared. Plugging all these numbers into the equation and solving for delta H yields -430.19 kilojoules per kilogram. This is the change in enthalpy from the entrance to the exit of the turbine, not either individual components. To determine the enthalpy of the vapor at the entrance of the turbine, utilize a steam table entry at 4,000 kilopascals and 300 degrees Celsius. As you can see, such an enthalpy is 2,961.7 kilojoules per kilogram. This means that the exit enthalpy is 2,531.5 kilojoules per kilogram. The vapor flow through the valve is isoenthalpic to the vapor flow through the exit. Thus, H2 equals H3 equals 2,531.5 kilojoules per kilogram. H3 refers to the valve enthalpy. Using thermodynamic information derived from a steam table for a vapor at 100 kilopascals, which is the exit pressure at the valve, we can find the enthalpies of pure water and pure vapor. The enthalpy of pure water is 417.51 kilojoules per kilogram, and the enthalpy of pure vapor is 2,675 kilojoules per kilogram. The enthalpy of evaporation is 2,257.5 kilojoules per kilogram, right in between. Obviously, the enthalpy we saw for above is that of a mixed vapor. Using this equation for vapor quality, X equals H minus HF all over HFG, we can solve for the vapor quality of the vapor, which yields 94% vapor quality. From the same steam table entry as above, we determined that the temperature of the vapor at the valve is 99.61 degrees Celsius. Returning to the last conceptual problem of the set, we are not able to determine the thermodynamic state of the vapor at the discharge of the turbine because no state property information was given, such as temperature or pressure. Had temperature or pressure been given, it could be determined.